So at some point in your life, you probably asked a question and somebody responded with, "Oh, I have a hypothesis about that," or "I have a theory." And that is one of the problems I think that we find with the scientific method. That the scientific definition of a hypothesis and a theory is very different from the way that we might use it in our normal lives. And when we use it in our normal lives, it's often something that's not supported, that we're just making a guess about. But the thing about a hypothesis is that it is a proposed explanation for a very specific question. And remember that I said that it's educated and plausible. That's not to say that you can't make an educated and plausible explanation to a question that you might have. I'm not saying that at all. I'm just saying that sometimes there's confusion between whether or not a hypothesis is something that's a guess or something that is an actual plausible explanation. So a hypothesis proposes an explanation for a very specific question. It is going to be answered by a very defined experiment. And so it answers a question in a very specific realm. A theory, however, is a very well-supported hypothesis. So it is a well-supported hypothesis that has been tested over and over and continues to be supported in a variety of situations. So a theory is also unlikely to be altered by new evidence. So it is so strongly supported that we consider it true, and true meaning in air quotes. And I say that because it can be disproven. You can find a situation where that theory doesn't hold up. Now, that doesn't mean that it's necessarily invalid or that it doesn't explain a whole broad area, but just keep in mind that theories might be disproven, but they're probably not going to be at this point. These are things that, as a biological or scientific community, we have set as essentially facts. But I do want to say that scientific hypotheses and theories are never proven. They are supported or not supported, but they are never proven. And so as you're doing your labs this semester, if you tell me that you have proved your hypothesis correct, I'm going to take off points, because hypotheses do not prove something, or an experiment does not prove your hypothesis to be true. It supports that it's true. And same thing with theories. They are supported, they are not proven. So our theories are not speculation or guesses. They are hypotheses of which scientists are most certain. They are repeatedly tested. They are supported by a large body of evidence. And they are broader in scope than a hypothesis. Meaning that they are hypotheses for a wide range of related questions. So a hypothesis becomes a theory when it's tested over and over and over. So a few examples of theories. Some of these are biology, some of these are not. One big one is the cell theory, and I actually already gave you the cell theory at the beginning of this lecture, and that is that all organisms are composed of cells. There's a little more to that we'll talk about next chapter. We've also got the theory of evolution by natural selection. We're going to talk about that in an entire unit, 2 chapters long. Another example is the germ theory. Now, the germ theory states that certain diseases are caused by microorganisms. So those are a couple of big biology theories. We've also got things like the Big Bang theory that explains the origin of life, and really that's actually origin of the solar system. We've got universal law of gravity, Newton's laws of motion, and laws of thermodynamics. Those are all theories that have been very heavily studied and very strongly supported. So once we have our hypothesis, once we have asked our question and proposed a plausible and educated explanation, we need to figure out what's going to happen. What data do we need to support our hypothesis? So we are going to devise a testable prediction for the outcome of our experiment. So we need to think about what we're actually testing. But the goal of the prediction is to propose a situation, aka data, that will give you a particular outcome if your hypothesis is true. So when you make a prediction, you're looking for what sort of data do I need to show that my hypothesis is supported. And if you discover that data, if you observe that data, then you know that you have supported your hypothesis. But the opposite might be true. If you don't get that data, then you know that you haven't supported your hypothesis. So we write our predictions in a very specific manner. Our prediction is written as an if-then statement. And that if-then statement makes it possible to determine whether you have supported your hypothesis or if you need to find an alternative one. So this if-then statement is going to be if our hypothesis. So you should have already written your hypothesis, and if you've written a correct hypothesis, your hypothesis is going to say nothing about the actual experiment or the data that you expect. You're just providing the information. But the prediction, the then half of this statement, you are going to predict specific data from your experiment. So again, you should have no data in your hypothesis. Your data is just the explanation. The prediction side of it is, what do we need from our experiment to support our hypothesis? So if we go back to our echinacea discussion, our hypothesis might be, if echinacea reduces the likelihood of catching the common cold and the duration of the symptoms. So there's our hypothesis. Echinacea reduces the likelihood of catching the common cold and the duration of the symptoms. Notice there's really no data in there. There's nothing that says anything about how we're going to test this or what we need to get, but it is providing an explanation. Then, and this is our prediction, individuals taking echinacea, so that's part of our experiment. We're going to give them echinacea, should get a cold less frequently. There's some data. So we've got a little bit of our experiment and a little bit of data. Then those not taking it, there's our experiment again. We're going to give some people echinacea. We're not going to give others echinacea. And when they get sick, their illness should not last as long. There's more data. Now, I'm actually not a huge fan of this experiment as an example because it's quite complicated. They're actually testing two different things at the same time. You kind of want to avoid that when you're designing your experiment. They are testing frequency and duration. It would be easier for us to understand and use this example if they would have just picked one for the explanation, but that's okay. Usually when you design your hypothesis, your experiment, and your prediction, you want to test one thing, but it is what it is, and we'll just go with it. So we've got our prediction. We need to measure the frequency and the duration. That's what we're measuring from our experiment. So let's talk about how we design an experiment. When we are designing our experiment, essentially we want to control as many things as possible so that we know the only thing affecting our outcomes are what we change or what we cause. So using controlled experiments where we set the manipulated values, we set the comparison, makes experiments more powerful. And the reason is that you generally have two different groups, at least two groups. One is your control group or your no treatment group. And the other is your group that receives the treatment. And in the most basic experiment, you now have a way to say, look, when we change this variable, this is what happens. This is what happens when it's not present. This is what happens when it is. So to start off with our experiment, we need to determine what we are going to subject our groups to. So we need to determine our treatment. This is the experimental condition applied to the research subjects. So this is basically, what are you doing to these subjects that you're testing? What are you interested in? Well, what is our question? Our question is whether echinacea decreases the frequency and the duration of the cold. So our treatment, our condition that we are going to apply is giving them echinacea. So we need two groups. We need one group, the experimental group, that is the subjects exposed to the treatment. So we need a group that gets the treatment. We also need a control group. This is a group that is treated in an identical way to the experimental group, except for one variable, and that is that they don't receive the treatment. So in this case, the control group I spelled that wrong, will not receive echinacea. I'm having trouble with that, and I probably still spelled it wrong. All right, so we're going to start with our control group, do not get the treatment, our experimental group that gets the treatment. So then we need to consider our variables. Now, there are different types of variables that we might need to talk about. Let's start with the dependent or the independent variables. So our variables are anything that will change in the experiment. The independent variable is the variable or the entity being studied. In other words, it is your treatment, and it is controlled by the researcher. In this case, our independent variable is going to be the dose of echinacea. Now, depending on how crazy we want to get with the experiment, it might just be a single dose and you get it or you don't. It might be varying doses of echinacea compared to no echinacea. But in this case, we're just going to simply say it is the dose of echinacea. The dependent variable is the variable that is observed or measured in the experiment. Another way to think of the dependent variable is that it is the data that is produced or affected by the independent variable. So the dependent variable is what we are actually going to measure, and we are going to measure the response to having echinacea. We also need to worry about experimental variables. So experimental variables are outside variables that could affect the outcome, or that could affect our dependent variable. And they are a really important feature of a good experiment. You want to minimize outside variables that could affect your experiment. So that's why we treat our control group and our experimental group as similarly as possible. We want them to have identical treatments. So controlling experimental variables is an attempt to minimize any difference. We want the only difference to be the treatment itself. Now, sometimes we have uncontrolled variables. Now, these are variables that you can't help. Sometimes you cannot actually control for them. Sometimes controlling for them is really hard. Sometimes you don't even realize that there's an outside uncontrolled factor that's affecting your experiment. So uncontrolled variables are things that the researcher cannot or chooses not to control. Now, we don't want these, but sometimes you can avoid them. So if you have uncontrolled variables, you need to make sure that you pay attention to how they might affect your data. So if we're thinking about this echinacea experiment and you have two groups of people, you might want them to be all the same age or all the same health, generally in good health. You might not want to test a medication on a group that's already sick. There are lots of things that you might control for in this echinacea experiment.